Good morning, ma'am. My name is Chiranteja. I'm from CSC AML, third semester, second year. Today, my topic is about Markov chain analysis for state transition probabilities in automobiles vehicle control. Introduction to Markov chain analysis in automation vehicles. Markov chain are mathematical models used to represent systems that transition between state with central probabilities. In automation vehicles control, they help model the likelihood of moving between different driving states. This analysis enhances decision making and improves safety and efficiency in automation negative systems. What is Markov chain? A Markov chain is a mathematical model that describes a system that moves between different states with certain probabilities. Why automation vehicles use Markov chains? Automation vehicle must constantly make decisions under uncertainty. With a predestinity continue walking or stop, will the lead vehicle brake suddenly? Will the road become slippery? Will an obstacle move into the lane? Markov chain give a mathematical method to predict next states, enabling safety planning, smoother control, anticipation of risk, understanding of dynamic environment. Fundamentals of Markov chain. A Markov chain contains a set of states that transition probabilities between those states. The key priority is the Markov priority when further state depend only on the current state. Transition probabilities are represented in a matrix known as the transition matrix which similar summarize the system dynamics. Defining state in automation vehicles. A state represents a situation that vehicle may observe or be in. Example of states: vehicle behavior state, traffic object behavior state, environment road state. The Markov chain allows the AV to estimate what comes next. States in automation vehicle control. States typically include driving modes such as cruising, stopping, turning, and obstacle avoiding. These states are defined based on vehicle behavior, sensor inputs, and environment present precipitation. Precipitation. Accurate state defining is critical for effective modeling and control strategies. Translation probabilities. A Markov model uses a transition matrix. If we have state S1, S2, S3, then Pij is probability of transition from state I to state J. Each row to 1 sums to 1. Interpretation: if a vehicle is slower, there is a 20% chance that it will start braking next. It predicts capacity is crucial for AV safety. Using Markov chain in control decision, Automation vehicles use Markov chain to estimate probable future trajectories of objects and choose actions that minimize risk. Predicting human driven vehicle behavior. AV predicts the probability that a car ahead brakes, lane changes, intentions, stop and go behavior. Pedestrian prediction states idle, walk, run, stop. Markov chain yields the likelihood of each. Weather and road surface prediction used for adaptive cruise control, braking distance estimation. AV model transitioning the AV itself transitions between drive modes, normal to caution to emergency braking. Markov chain decides when transition should happen based on risk level. Transition probabilities and data collection. Transition probabilities are estimated from real world driven data or simulation. Data collection involves recording state changes over time in various driving scenarios. Reliable estimation of these probabilities is essential for accurate modeling and predicting. Building the transition matrix. The transition matrix is constructed by calculating the frequency of state transition or collected data. Each entry in the matrix represents the probability of moving from one state to another. The matrix must satisfy the properties that each row sums to 1, ensuring valid probability distribution. Hidden Markov model HMM. Often true states are not detected observably. Example, a car intent to turn cannot be directly seen. Only signals like trajectory curve, blinker activation, speed reduction. HMMs allow the AV to estimate hidden state using observed scenario sensor data. Hidden state to intent, observed state to speed, position or pose, pause state. Applications in automation vehicle control. Markov chain model are used for path planning by predicting likely future states. They aren't in risk assignment by estimating the probability of unsafe or undesirable states. Control algorithm leverage this model to optimize driving decision under certainty. Markov decision process MDP for control. When AV must choose the best action, Markov chain extend to MDPs. Components of the MDPs: state, action, transaction probability and reward. MDPs allow finding a policy. Example, slowing down because probability of consoling is greater than threshold. Changing lane because probability of lane blockage increases. MDPs are central to AV behavior planning. Multiple step predictions. Markov chain compute future states. Step 1 P, step 2 P square and step is P power K. Example, predicting whether a A pedestrian will settle be in the crosswalk 2 seconds from now. This helps AV plan braking, choose lane changes, avoid consolation proactively. Advantages of Markov chain analysis: provides a probabilistic framework to handle uncertainties inherent in dynamic environments, enables quick computation for further states, responsibilities for real-time decision making, facilitates adaptive control strengths that can learn and update transitions probability over time. Limitation and challenges: the Markov assumptions may oversimplify real world dependencies that influence vehicle behaviors. Large state space can lead to computational complexity and data separately issue. Accurate modeling requires executive data collection and continuation updates to reflect changing conditions. Conclusion and summary: Markov chain analysis offers a powerful tool for modeling state transitions in automation vehicle control. It supports safer and more effective navigation by quantifying transition uncertainly. Consider researching and integration with advanced AI methods will further improve automation driven systems. Thank you, ma'am. Thank you for listening me patiently. Thank you.